Let's continue our discussion on the partial derivatives. So we have here the partial derivatives viewed as rates of change and slopes. So recall that if y is a function of x, then the value of f prime of x sub 0 can be interpreted either as the rate of change of y with respect to x at x sub 0 or as the slope of the tangent line to the graph of f at x sub 0. Partial derivatives have analogous interpretations. So to see that this is so, suppose that C1 in the is the intersection of the surface Z. So we have here C1. So here is our C1 is the intersection of surface Z equal to f of x y with the plane y equal to y sub 0. Okay, so this is our plane y to y sub 0, this plane here. Okay, this plane. And that's C2. So this C2 here. So C2 is the intersection or its intersection with plane x equal to x sub 0. Okay, so this color blue here, this plane color blue, here also color blue. So that is the plane y equal to y sub 0. So this is our plane x equal to x sub 0. So in this big figure, thus the partial derivative of the function of x and y, where y is held constant equal to y sub 0 with respect to x, can be interpreted as the rate of change of z with respect to x along the curve C1. Okay, along the curve C1. And f sub, or the partial derivative of the function of x sub 0 y and y with respect to y, where x is held constant at x equal to 0, can be interpreted as the rate of change of z with respect to y along the curve C2. This is our curve C2, the color orange. C1 is also the color orange. In particular, the partial derivative of the function at a particular point with coordinates x sub 0 and y sub 0, so with respect to x, is the rate of change of z with respect to x along the curve C1. Okay, this is our curve C1, the orange. At the point x, the point coordinate with the coordinates x sub 0, y sub 0. Okay, so these are coordinates. This is our point with these coordinates. And partial derivative of the function at this particular point with coordinates x sub 0, y sub 0 with respect to y is the rate of change of z with respect to y along the curve C2. So curve C2, the color orange class. Okay, at the point with the coordinate x sub 0, y sub 0. Okay, this point here with coordinate x sub 0, y sub 0. Alright, so this is what we call the slope. Slope is uh, the partial derivative of the function of two variables x and y at the point x sub 0, or at the point with the coordinates x sub 0, y sub 0. Okay, so this one. So this is the slope. So the slope is the tangent line, tangent to the curve C1. Alright, so we have here the plane, the z, which is equal to function of x and y. And also this one is also the slope. So this is the slope, no, with this figure at C2. Oh, this is a plane C2 or curve C2 intersecting this plane here. That is x equal to x sub 0. The color blue intersecting the color orange. So this is the point, the line that is tangent to this point of intersection between this plane x equal to x sub 0 and the curve C2 is what we call the slope given by this expression f sub y of x sub 0, y sub 0. Okay, similar to this one. So in applied problem, the interpretations of the partial derivative of the function with respect to x at this particular point with coordinates x sub 0, y sub 0, and also the partial derivative of the function with respect to y at this same particular point with coordinates x sub 0 and y sub 0 must be accompanied by the proper units. So we'll see that in our example number 4. So in our example number 4, so let's recall that the wind chill temperature index is given with the formula W is equal to 35.74 plus 0.6215 T plus the quantity 0.42 or 0.4275 T minus 35.75 gross quantity times V raised to power 0.16. So this is the wind chill temperature index. Okay, so this is given in this formula. So now we are asked to compute the partial derivative of W, the wind chill temperature, with respect to V at the point with the coordinates T and V, where T is equal to 25 and V is 10. And interpret this partial derivative as a rate of change. Okay, so this is our example number 4. So now I'll show you the solution to this problem. So this is what is meant by this statement here. That in a problem, in an applied problem, the interpretations of this notation and this notation must be accompanied by the proper units. Okay, so we have here the units in terms of temperature, degree Celsius or degree Fahrenheit. All right. So wind chill temperature, so that should be in terms of degrees Fahrenheit or Celsius. Okay, so the solution to this problem. So we are going to compute now the partial derivative of the wind chill temperature index with respect to V. So it means that we hold T here as constant. Okay, holding T as constant. Then we can apply the rules in differentiation. Okay, so we treat here or held T as constant. Okay, so differentiating with respect to V. So we have here holding T fixed or constant, they're just the same class. And differentiating with respect to V, so it yields. Alright, so we have this notation here. Partial derivative of W, where W is our wind chill temperature index with respect to V. Okay, so this is the notation class. So TV is equal to, so this is constant. So derivative of the constant is equal to 0. Okay, so derivative of a constant. So the first term here is constant. So this is equal to 0. So when you take the derivative of that, so that is equal to 0. Okay, so that's why we have here the first term is 0. And t is constant multiplied by a constant. And then you take the derivative of the second term. So this is constant. So therefore, this is also equal to 0. Alright, and then so the only remaining part here that we can differentiate, so this part here, we have this difference of two numbers. We still have t here, minus, multiplied by v raised to the power 0.16. Alright, so we will apply here the power rule. So applying the power rule, so this will be, so this will be the result class. So we have 0.16 minus 1, so this is negative 0.84. That's the resulting exponent after you subtract by 1 using the power rule. So this one here. Okay, so the 0.16 will go down. Okay, and then you multiplied it by the whole thing here, difference of this number. Okay, then since W is in degrees Fahrenheit and V is in miles per hour, so a rate of change of W, or the windshield temperature index, with respect to V will have a units of degree Fahrenheit per mile per hour, which may be written as degree F times H, means this is then per mile. All right, so because this is denominator fraction, so rules of multiplication fractions, so this will go up, then proceed to multiplication. That's why we have here Fahrenheit hour per mile. So that's the unit. Then substituting T equal to 25 and V equal to 10, so this will give us, no, you substitute it here. Okay, so you substitute this given value. Okay, because in the problem we're given the value for T and V. So after differentiating the function, taking the partial derivative of the function, we have this result. Then after that, you substitute the given T equal to 25 degree Fahrenheit and V equal to 10. That is miles per hour. Then you'll get this result that is approximately equal to 0.58 degree Fahrenheit per mile per hour. So this is as the instantaneous rate of change of the windshield temperature index with respect to V at this particular point, with temperature at 25 and V equal to 10. So we conclude that if the air temperature is constant at 25 degree Fahrenheit and the wind speed changes by a small amount from an initial speed of 10 miles per hour, then the ratio of change in the windshield index to the change in the wind speed should be about negative 0.58 degree Fahrenheit per mile per hour. Alright, so this is an application to our topic on partial derivatives. So I hope you understand this one, class. And thank you very much, and see you in our next example. Bye.